Welcome to this explainer. Today, we're diving into something truly fascinating, the intersection of ancient agriculture and cutting-edge medical engineering. We're going to look at how a plant that we've literally cultivated for thousands of years is on the brink of completely revolutionizing the highly technical world of prosthetics and implants.
But first, we have to ask a pretty provocative question. What if the very materials saving our lives are quietly harming our bodies and the planet? You see, right now, modern medicine relies heavily on petroleum-based plastics, stuff like ABS, nylon, and polypropylene. And look, for decades, these were the gold standard. They were cheap, light, mass-produced. But recent data is exposing a massive hidden toll. Fundamentally, on a structural level, they're flawed.
So here is our roadmap for today. We'll start with the plastic crisis, then we'll look at hemp cellulose as a new solution, move into 3D biomimetics, break down the biocompatibility data, and finally envision a carbon-negative future. Let's get right into it. Section 1. The plastic crisis and the hidden failure of petroleum-based polymers.
Okay, so right now we are undergoing this massive philosophical shift in material science. The old way of thinking basically treats prosthetics as isolated, dead shells. They just sit there trapping moisture and fighting against natural forces in the body. But the future is all about active biological composites. We're talking about materials that dynamically interact with our tissues. They offer microporosity to actually let your skin breathe, providing natural thermoregulation. It's a total game changer.
To understand why this is so critical, just look at the thermodynamic instability of those traditional synthetic plastics. When a patient walks on a standard prosthetic, they're applying cyclic stress, and within just 10 to 50,000 steps, which really isn't that much, microscopic cracks inevitably start to form. These turn into microdefects, which then leach microplastics and endocrine-disrupting chemicals, like bisphenols, directly into the surrounding tissue. And that's all while piling up millions of tons of unrecyclable medical waste every single year.
And the impact certainly doesn't stop at the human body. The planetary cost is staggering. Get this. Manufacturing just 1 single kilogram of medical nylon pumps up to 9 kilograms of carbon dioxide straight into our atmosphere. Now, scale that up to the roughly 40 million prosthetic users globally, and you can see how that carbon footprint becomes completely, utterly unsustainable.
Which brings us to Section 2, hemp cellulose, and engineering a plant-based alternative. So, where do we find a better way? Well, the solution actually lies in agricultural waste, specifically the discarded stems, or herds, of industrial hemp. Scientists have engineered an incredibly biocompatible resin called Hemp Med Plus. As you'll see, 70% of it is made up of long chains of hemp cellulose, which act as this incredibly powerful reinforcing framework that's bound together by a bio-based PLA matrix with just a tiny 2% touch of esterified glycerin for flexibility. It's a 100% plant-based, non-toxic recipe, no petroleum in sight.
Now, you might be wondering, how on earth do you turn a tough plant stem into a medical-grade 3D printing filament? It happens through a precise, 4-step extraction process known as green delignification. First up, mechanical separation. Then, the material gets a hot alkaline soak at 120 degrees Celsius, followed by a chlorine-free bleaching process using hydrogen peroxide. Finally, acidification. This whole process safely strips away the natural lignin, the glue of the plant, without destroying the hyper-strong crystalline structure of the cellulose itself. And honestly, plant biology is sheer genius. If we zoom into the microscopic level, these long glucose chains are bound together by a dense network of hydrogen bonds, forming this beautiful spiral angle of roughly 6 to 8 degrees. This geometry is an absolute marvel of millions of years of evolution. Because of this specific architecture, instead of instantly cracking like a brittle piece of plastic, the fibers absorb and dissipate impact energy. It behaves a lot more like a microscopic steel cable than a fragile pane of glass.
Moving on to Section 3, 3D biomimetics, where algorithms meet nature.
Having strong fibers is fantastic, but it's really only half the battle. This is where generative design enters the chat. Using advanced engineering software, designers can input the exact physical forces that a prosthetic is going to face out in the real world. Then, the algorithm calculates the physics and literally grows a biomimetic shape, imitating organic structures like bone or wood. It places material only where the stress lines demand it. This creates these incredibly complex geometries that are just physically impossible to make with old-school injection molding.
By generating internal structures like gyroid or diamond lattices, we can perfectly mimic human trabecular bone, dense on the outside, spongy on the inside. This allows the prosthetic to bend naturally with movement, all while slashing its overall weight by up to 70%. And here's the coolest part. The 3D printer actually rotates its nozzle while it's building, aligning those hemp fibers perfectly parallel to the incoming forces. It's essentially mimicking exactly how human muscle fascia grows in nature.
Let's check out Section 4, biocompatibility, and the hard data proving hemp's superiority.
All right, let's look at the numbers, because in rigorous stress tests, the mechanical superiority here is just undeniable. The HempMed Plus composite reaches a tensile strength of up to 170 megapascals. That completely eclipses standard medical-grade nylon and ABS plastic. In fact, it gives this plant-based material a strength-to-weight ratio that rivals even low-grade carbon fiber.
Pretty amazing, right?
But raw strength is really just the beginning. When put through cyclic bending tests simulating 1 million steps, this hemp lattice loses only 5 to 8% of its stiffness. Meanwhile, ABS plastic degrades by up to 30% or more. And most importantly for patient health, the hemp composite provides a naturally breathable surface that's slightly acidic, matching human skin's natural pH of 6.2. Combine that with a Class 0 cytotoxicity rating, and you are guaranteeing zero inflammation, zero allergic reactions, and absolutely zero toxic chemicals leaching into the body.
Finally, Section 5, a carbon-negative future and decentralizing the global medical supply chain. This new model fundamentally reimagines how we manufacture medical devices. Instead of shipping heavy plastics all over the globe from centralized factories, we can build hyper-localized supply chains. Imagine this: a local farm grows the hemp, a regional plant processes the agricultural waste, and a hospital hub 3D prints the personalized prosthetic on demand, all within about a 300-kilometer radius. This drops the cost of a prosthetic from thousands of dollars down to roughly $120 to $300. Plus, it completely eliminates those massive logistical carbon emissions.
What this means is we're turning medical manufacturing into a deeply regenerative process. Just think about this. While it's growing, a single hectare of hemp absorbs up to 15 tons of carbon dioxide per season. And because that carbon gets permanently locked into the cellulose framework of the prosthetic device itself, the entire life cycle becomes carbon negative. We are quite literally pulling carbon out of thin air to help a patient walk.
We are truly standing at the threshold of a new material age. So, as we wrap up this explainer, I want to leave you with this question. If we have the technology right now to make life-saving medical gear that heals both the patient and the planet, why in the world are we still settling for toxic fossil fuel plastics? Thank you so much for exploring this vital shift with us today.